Hello again. This is video lecture 22.4, and we're going to talk about chapter 22, section 5, and we're going to calculate the electric field due to a charged disk. So that's a filled-in circle with charge smeared out uniformly across it, and it's a two-dimensional distribution. Okay. We're still talking about the electrostatic field due to what's called a continuous charge distribution, meaning it's just not a point particle. You can't treat the thing as a particle. Here we have this disk. You can see the picture of it down below. We're going to take some total charge, let's call it Q, and spread it out uniformly over this very thin disk of radius r. That's what the blue circle is that you see down there. It's really a disk filled in. And the total charge Q is painted evenly across that whole surface in blue. And so you can talk about the surface charge density. Remember, that would be in units of Coulomb per meter squared, because it's a charge per unit area, and that symbol is a lowercase Greek letter sigma. And it would be the total charge of the whole disk, Q, over its total area. A disk has area pi times radius squared. Okay, so every point on that disk has the same value of that surface charge density sigma. Here's our task. Notice, by the way, we've set up the geometry in a very specific way so that we can do the math. We have put the disk in the xy plane with its center at the origin. Therefore, the z-axis is perpendicular to the disk going through its center, and the plus z-axis is going up. So the negative z-axis, by the way, would go down below the disk. And then we have picked an arbitrary point P on the z-axis that is a distance z from the origin. And we want to find the electric field E at that point, P. What is E vector at that point, P? Okay, again, let me emphasize. The disk is not a particle. It doesn't look like a particle. You can't treat it as a particle, except in one special limit. If the point P happens to be very, very far away from the disk, so that the distance z is much, much larger than the radius r, then it should act like a particle. But that's a special case. We have to find the electric field here at a point P that could be indeed quite close to the disk, and therefore we cannot treat the disk as a particle. Instead, we're going to have to do the three-step process for a continuous charge distribution, which I talked about in the previous video lecture and in the previous class. The three steps for finding the electric field of a continuous charge distribution are: after you realize that you can't treat that distribution that you have as a particle, you imagine, step one, you imagine dividing up the object into an infinite number of infinitesimal pieces. And you use the known electric field for that piece. Call it dE for each little piece. And then you add up all the little dE vectors to get the total. Now, usually the little piece you're talking about is just a little point particle. But not always. And I'm going to show you right now with this case what that dE is going to be looking like. So here's the first step. We have to imagine dividing the disk up into little pieces. But what we're going to do here is break it up into an infinite number of infinitesimal pieces, each of charge dq, and to take advantage of the geometry of the disk and the known result for the electric field of a ring. Okay, a ring is like a hollow disk, right? A ring is something that you can put your finger through. Okay? A disk is not something you could put your finger through. But we know the electric field on the perpendicular axis of a ring. We already know that. We did that already. So we're going to divide up the disk into an infinite number of nested rings. This drawing shows one of them. Okay? So we're taking each tiny piece of the disk to be a ring. Okay? And we can divide up the object we have, in this case a disk, into the tiny pieces however we see convenient. And we're saying it's convenient in this case for the disk to divide up the disk into little rings. So just to be clear, let me come over here to the side. That's my view of the disk. And then let me show some of these rings. There's just the center point of the disk. The ring has a little tiny bit of thickness like that. Okay? That's one possible ring. Now the next one would be just another ring layered just a little farther out from the first one. Let me shade that ring in a different color. All right, that's the next ring. And then the next one farther out. Okay, shade it in. And of course you have inner ones too. You got one a little bit closer in. Okay, getting the idea? An infinite number of nested infinitesimal rings, which get larger and larger radius until you've created the whole disk from the rings. That's what this drawing here is showing. And what it has done, it has picked quite arbitrarily one of those rings to draw right there. And the ring that they have picked has radius little r. Let's be clear, little r. See it in the picture? Don't confuse that with big R, which is the radius of the disk. We've got a disk in this problem, and we've got a bunch of rings, plural. Little r is the radius of this particular ring that you see. But the ring also has a little bit of thickness or width to it. And that amount, because it's tiny, is labeled dr. Right? That's the width of the ring. Okay? All right, now, this whole disk, of course, has a surface charge density sigma. Okay? So we have a disk with uniform surface charge density sigma in Coulomb per meter squared. And now I've taken that little ring right there. I've drawn one of my rings, it's a little flat-topped ring, and I want to know how much area it has. So this is a ring with area what? How are we going to think about this area and so forth? This usually takes all getting used to. First of all, it's a tiny amount of surface area because it's just that shaded area that you see there in the picture. Ignore thickness, it's completely two-dimensional, not three, two-dimensional. So the area I'm talking about is the area that's shaded there. How much area is that? It's going to be a tiny amount, so I'll call it dA. Well, don't overthink this when you have these little infinitesimal dimensions like dr. The area shaded is the distance around times the thickness or width. So the distance around is the circumference of that ring, 2 pi times little r, the radius of that ring, and its thickness is dr. Right? This dimension around times the thickness, dr. 2 pi r dr. That's the area of that ring. Now I want to have an expression for the amount of charge that that ring has. Just that one highlighted ring. It's going to be a tiny amount of charge, because it's a tiny ring. So we'll call it dq. All right, now here's where we use the surface charge density sigma. Because to get the area of that ring, I'll take the surface charge density of the disk, same everywhere on the disk, sigma, and I'll multiply that by the area of the ring. Remember, sigma is charge per unit area. So that is sigma times 2 pi r dr. And now we have a nice little symbolic expression for the charge on a ring as a function of its radius. All right, so that highlighted ring is the tiny piece of the disk that we're now going to write down the electric field for. All right, here we go. So, step 2, find the electric field, we'll call it dE arrow, at point P from each piece. Okay? All right. That's what this picture shows. It shows the disk. It shows the particular ring that we have selected of radius r and thickness d, radius little r and thickness dr, that the point P is height z above the center, and we want to know the electric field at point P from that ring. But we already have the result for the electric field of a ring. Let me remind you of that, okay? Electric field on perpendicular axis of a ring. Well, I'll say this, of radius little r and total charge big Q. I'm just going to use the result that we derived in the previous video lecture and used in the previous class. Right now I just want the magnitude of the electric field at point P. Well, due to a ring. It will be the magnitude of the charge Q times the magnitude of the value Z over 4 pi epsilon 0 times Z squared plus R squared to the 3/2. But now what I have to do is I have to apply this result to the highlighted ring in my drawing over here. I have to figure out how to use that result that we already derived for the particular ring in our drawing here. Okay, first note, I'm going to change the E magnitude on the left to just this, dE. Now why dE? Because it's electric field coming from a tiny amount of charge. That ring has charge dQ. So I'm going to call the field from it dE. And I'm going to change the Q magnitude there to dQ, because that's the charge on the ring, times Z over 4 pi epsilon 0 times Z squared plus R squared, or R squared plus Z squared, to the 3/2. Okay? Now, let's just keep working on this a little bit. dE equals, okay, for the dQ, use that expression right there that's highlighted. Sigma times 2 pi r dr, 2 pi little r, d little r. And I've already got a z up there too, don't lose that. So what I have upstairs is 2 pi sigma z r dr over 4 pi epsilon 0 Z squared plus R squared to the 3/2. Understand what I did? For the dQ, I took sigma times 2 pi r dr, and of course that was multiplied by Z. Okay, that's step 2. We picked a tiny piece of the disk. We picked a piece we decided to pick a piece that was ring-shaped. We used the result we already had for the electric field on the perpendicular axis of a ring to write down the electric field dE on the perpendicular axis of this ring. And note we already know, assuming that this disk is positively charged, that the electric field contribution from the ring that we're highlighting is straight up the z-axis away from the ring and the disk. And that's the same direction for all the little dEs from all the little rings that, when nested together, make up the disk. Okay? All right, now step 3 is the adding, which amounts to integrating. Use the principle of superposition to sum up all the contributions from all the pieces of the disk, all the rings, to get the net electric field at point P. This is vector addition, and this answer is the physically real field that you would measure at point P. Well, the good news here is every ring that makes up this disk produces an electric field on the perpendicular axis that points straight up. So all the dEs just point straight up. So all we have to do is add their magnitudes. This is where, in one case, where the vector addition is easy. Okay, so that's what I'm going to do next. For all rings that make up the disk, the dE vectors point in the plus z direction, assuming that the charge on the disk, which in this case you could represent by sigma, charge per unit area, is positive. Okay, so to get the net electric field at point P, magnitude, which I would just denote like that, E, I add up all the little dEs from all the rings, and that means integrate. So you see that expression right up above for the dE, that's what I integrate. 2 pi sigma z r dr over 4 pi epsilon 0 times z squared plus r squared to the 3/2 integrate. Well, we better simplify, shouldn't we? Look, I've got a pi upstairs and downstairs. I've got a 2 upstairs that'll take 2 out of that 4. Okay? All right. Now, what are the limits of this integral? It's a definite integral. Well, I'm integrating over the radial coordinate of the ring. Right? See it right there? Right there. For the ring we drew. That's the little r, right? The distance from the center out to that ring. Well, we have to take all the rings that together make up the disk. And they're nested, starting right up there at the center and then going outward. So you have to think about what the little r varies over to go from the middle out to the edge. And little r is just the distance from the center, so when you're at the center, the little r is 0. And when you're at the edge, the little r is equal to big R, the radius of the disk. So my limits on my integral are little r goes from 0 to big R. And now we need to talk about what quantities can be brought out front of the integral. You always have to ask that. You get to bring out any quantities that would have the same value for every ring, because that's what you can think of as being constant. If it's a quantity that has the same value for every ring that you could pick inside that disk, then you can bring that quantity out front. For example, every ring has the same surface charge density sigma. That can come out. Every ring has the same z, because that's just the distance up the z-axis from the center to point P. And, of course, epsilon 0 down there is a constant. Okay? All right, so what we can bring out front, and the 2, of course, I beg your pardon, the 2 can obviously come out front. What's left to come out front? Sigma z over 2 epsilon 0. Then I have the integral from 0 to big R of r dr over z squared plus r squared to the 3 halves. Note you can never bring the d blob out front of an integral. That's just nonsense talk. I can't bring this little r out front because different rings have different little r's. And I can't bring that denominator out front because it's got a little r in it. So that's the integral I have to do. But as I do this integral, the z squared I can think of as being a constant. All right, I'm going to call that integral big I for integral, so that my expression now for the total electric field magnitude is sigma z over 2 epsilon 0 times the result of that integral, big I. And now we just have to spend a little bit of time talking about how to figure out the result of that integral, big I. Okay? Well, you have a couple of ways you could do it. Big I means integral from 0 to big R, little r dr over z squared plus r squared to the 3 halves. One option is to go into Wiley Plus, your book, click on Read, Study, Practice, click on the drop-down menu that shows all the chapters, click on Prefaces and Appendices, click on Appendices, and go to Appendix E, and look for, and then scroll to the table of integrals, and look for the integral that has this structure. You got to be able to recognize the structure, and it'll be given as an indefinite integral. And the structure will be x dx over constant squared plus x squared all to the 3 halves. It uses the symbol x. And the constant squared, I think, is an a squared. But that's the structure. It turns out that its integral, they're numbered in this table, 18 in Appendix E in your book. But I'm going to actually do the integral with you here. Now, if you don't want to go through this, feel free to fast forward. But it might be good practice if you're feeling a little uncertain about doing integrals, because it's something that we actually can do. Okay? Let's actually do this integral I've labeled I together. What method would we use, I wonder, to do that integral? Because there's an r in the numerator, as well as the r squared downstairs, I'm going to do a u substitution. Let's let u equal z squared plus r squared, where I think of z squared as a constant. Then the differential of both sides, du, the z squared is a constant, I'll have 2 times r times dr from the right, because it was r squared. So I get 2 times r times dr. That means that r times dr is equal to du over 2. And so back up in my original integral, where I have an r dr upstairs, I can replace it with a du over 2. And then downstairs, where I have this z squared plus r squared, I can just replace it with u. So now the integral I looks like this. Okay, I'm bringing the 1/2 out front. I have a du upstairs and a u to the 3 halves downstairs. Let's put the new limits on the integral. Now these are u values now, right? And you figure out the u limits by taking the r limits you had in the original integral, 0 to big R, and then this formula that defines u. So to get the lower limit for u, plug in the lower limit for little r in the u formula. Little r equals 0, so the lower limit of u is z squared. For the upper limit in the r integral, the upper limit is big R. Substitute that for the little r squared in the u formula, and you get u equals z squared plus big R squared. And now you've got your integral to do. Now I am going to write it like this. 1/2 integral from z squared to z squared plus big R squared. I'm going to write it like this. U to the minus 3/2 power du, right? Same thing, I just took it upstairs and made the exponent negative. Then I just need the fun little result for that integral, because that's the structure I have, u to the n power du. That's like the first integral you learn. U to the n plus 1 over n plus 1. Where for us, the n is negative 3/2. So let's see what we get. Now don't forget this 1/2 out front. So we'll have u to the n plus 1. Now again, n is negative 3/2. Negative 3/2 plus 1 is negative 3/2 plus 2/2. That's negative 1/2 over n plus 1 over negative 1/2. Well, I have a 1/2 upstairs and a negative 1/2 downstairs. That means out front what I really just have is a negative 1. And u to the minus 1/2 is 1 over the square root of u. So there's what it is. Minus 1 over the square root of u. And then I put in my limits. Lower limit is z squared. Upper limit is z squared plus big R squared. So let's put those limits in and see what we get. Minus bracket. Okay, for the upper limit, I substitute z squared plus big R squared for u, and that u is inside a square root downstairs, so that we have that. Minus 1 over square root of z squared, which we can write as minus 1 over square root of z squared plus r squared minus 1 over z. Or, distributing the negative sign through, we get 1 over z minus 1 over the square root of z squared plus r squared. There's the integral I, that whole thing. And that goes back up there for the electric field. Okay, and we've got the result. I'll write it down for E, the result for E. Okay, I had a sigma z over 2 epsilon 0 out front times I. 1 over z minus 1 over square root of z squared plus big R squared. Now, we could leave it that way, but most physicists would reduce this algebraically to make it a little bit simpler. And the way to do it is to take that quantity inside the brackets, think of it as a subtraction of two fractions, and get a common denominator. And the common denominator is the product of those two denominators. So that's z times the square root of z squared plus r squared. That's the common denominator. Then in the numerator, figure out what goes. Well, first term has to be multiplied upstairs and downstairs by a factor of square root of z squared minus r squared. Then minus. And the second term numerator has to be multiplied by z. Now, when I do that, notice there's a z out front upstairs and a z the inside downstairs, so that cancels. And actually then, what I've got out front is sigma over 2 epsilon 0. And now what's left inside the brackets? Well, the first term is square root of z squared plus r squared over square root of z squared plus r squared. That's just 1. And then I'm left with minus z over square root of z squared plus r squared. Ta-da, that's it. That's quite interesting looking, isn't it? But that's the result. So let's summarize that with the next slide. Okay. So there's the picture of the disk again. In the xy plane, center at the origin. Got the perpendicular axis is z, point P. The thing has a total charge Q, radius big R, surface charge density sigma of Q over pi r squared. I'm going to write down my answer now for the electric field at point P in terms of a magnitude and a direction. First, the magnitude of the field, magnitude only. Notice that notation. Okay, notice what I've written out front. I took my answer right up above and I just put absolute value on the sigma. Absolute value of sigma over 2 epsilon 0. Why? The disk could be negatively charged. If the disk is negatively charged, sigma is negative. Then, in brackets, 1 minus absolute value of z over z squared plus r squared. Why absolute value of z? Because then the formula is also valid if point P, like there, is below the xy plane. Because it's absolute value of z in that formula. Okay? So this is on the perpendicular central axis above or below the disk. Now that's the magnitude of the electric field. We still have to get the direction. And that's easy. The direction of E is perpendicularly away from the disk if the sigma, surface charge density, is positive, and perpendicularly toward the disk if sigma is negative. And now we have the field of a disk. Okay? And that's the formula for that. So we're getting all these different fields, and it may seem kind of like odd, but we're just picking common shapes. And unfortunately, the electric field result for different shapes is different. So we've studied a complete circular ring, a circular arc, which is part of a ring, a straight line of charge, like a pen or a pencil, a stick, and now a disk of charge. And actually, I can use my formula, my answer for the disk field case, this one we just did, to get another answer out, almost for free, as a bonus. Special case. What if we have an infinite planar sheet of uniform charge density sigma? What do I mean by that? Just imagine that disk I've drawn in the picture, the blue disk in the xy plane, and imagine its radius r grows to infinity in all directions. All directions. That makes sense what I'm saying? Okay? Let the radius of the disk go out in all directions. You will then fill the entire xy plane with this charge density sigma. Don't worry about how that doesn't seem like that's plausible. Okay? We'll discuss when, actually, believe it or not, this situation can actually be used in the real world. But for now, I'm just saying, imagine letting the radius of this disk go out to infinity in all directions so that the disk fills the entire xy plane, and every part of that disk has the same sigma. So all you have to do is take our answer that we just got for the electric field of the disk and take the limit as big R goes to infinity. Okay, so look back up here and see what you get in the limit where big R goes to infinity. You get an amazingly simple answer. Since that big R down there has gone to infinity, I don't care what the z squared is. The denominator there is infinity. Z over infinity is 0. So what's in the brackets is 1 minus 0. 1. So all that survives is what's out front. Sigma absolute value over 2 epsilon 0. And that's the electric field magnitude of what's called an infinite planar sheet of uniform surface charge density. Notice that this formula for E in this special case doesn't depend on Z, right? There's no Z in here. The field magnitude is the same no matter how far away from the sheet you are. That means you get a uniform, it's called a uniform electric field. It's the same everywhere. It doesn't get any weaker if you go farther away. if it truly is an infinite sheet. I've in fact drawn, or I've had Mathematica draw, some electric field vectors for an infinite sheet. The infinite sheet is that kind of pinkish flat region in the xy plane. And then the z-axis is perpendicular to the sheet. And every point on, this is a positively charged sheet, every point on the top has an electric field pointing up, and every point above the sheet has an electric field pointing up, and every point below the sheet has an electric field pointing down. And no matter where you are, above or below, the electric field has the same magnitude. So if you're here, it's up at magnitude sigma over 2 epsilon 0. If you're up here, it's the same magnitude and direction, sigma over 2 epsilon 0. Okay? It's the same everywhere. Okay, here's a good place for you to pause and take a break if you wish to, but I do have one more topic to talk about, and then you can come back, right? Just letting you know, because there's one more section I want to talk about. It's actually not any new physics, but we need to talk about it a little bit so that you can get used to it. We want to talk now, chapter 22, section 6, about what happens when you take a point particle with charge and place it in an electric field. Basically, we want to be able to predict how that particle will move. That turns out to be very important in physics applications, right? So the key idea is the motion of a charged particle in what's called an external electric field. What does that word external mean, that adjective? Well, if I have a charged particle that I plop down somewhere and let go, and I want to know how it's going to move, it's going to be affected by what electric fields are already there, even though this charged particle itself creates its own electric field. But this charged particle's own electric field cannot exert a force on this charged particle. It can't exert a force on itself. Okay? So the external electric field of this means we're talking about the electric field that's there already and is not due to this particle. We're just putting this charged particle in this so-called external electric field. This external electric field is already there because there's some charges in some configuration that are already present and already producing electric field, and we're taking our charged particle Q and immersing it in that external electric field. How will the charged particle move? Okay, so what do we need to be given to answer that question? We have to be told what is that external electrostatic field, E. We have to be told what's the charge Q of this particle we're immersing in the field. And, because we're going to need to use Newton's second law, we'll need the mass of the particle. We'll also need to know the particle's position and its velocity at a certain point in time, which we usually take to be time 0. Okay, that's the stuff we have to be given. And then here's the plan. First, find the electrostatic force on your particle. How? Remember this wonderful formula. F electric equals Q times E. Very, very, very handy in this chapter and later chapters. It says, if you already know the electric field E at a point, and you've got your charge Q and you're going to put it there, this is the way to get the force on that charge. Take the charge times what the field was. Then, apply Newton's second law to find the particle's acceleration. Remember, A arrow equals F net arrow over M, where F electric will be in that F net. It may be the only term in F net, it may not. It depends on what other forces are acting. Now, the resulting motion of the particle can be complicated. So let me look over here at this picture. Here we have an external electric field that is created by a charge distribution that we have already studied in some detail. An electric dipole. It's got a charged particle with charge plus Q, happens to be on the left, and an equal but opposite negative Q on the right. And you can see some field lines for that charge distribution. We've drawn those before. That's the external field, capital E. Okay? That's already there. Already there. Now you come along with your pet particle. And it's got some charge, little q. Okay? And your pet particle's charge, little q, happens to be, let's say, negative. And you put that particle right here and let go. Right? We would want to be able to know what it's going to do. Well, first, I'm going to just show you using F electric equals Q times E that we already know the direction of E here. It's tangent to the field line through this point and in the direction of the field line. Well, the field line's going away from the plus Q and towards the minus Q. So up here, the E, where the particle is to the right. That's the direction of E. So I take Q times E to get F electric. But remember, Q is negative. I decided to do that just to test us. And so this Q right here is negative scalar. If I take a negative scalar times a vector E, I get a new vector, in this case F, in the opposite direction to E. And that's why the F electric on our particle is shown exactly opposite to E. And if that's the only force on our particle, which is probably the case, then that from Newton that's F net, then that's the direction of A, the acceleration. So the particle, when I let go, will start to move to the left. But warning, that doesn't mean that its trajectory will follow this field line. A lot of people want to say that. No, not necessarily. The trajectory will probably be more complicated than that. Okay? But basically, you've got to know the external field E already, know the charge and mass of the particle you're going to immerse, and where you're going to immerse it. Use F electric equals QE to find F, and then use A equals F net over M to figure out how the thing's going to move. And I want to show you last thing I want to do here is show you a Wiley plus animation of the motion of a charged particle in an external electric field. So let me go to Wiley plus, and now you're looking down from above on the XY plane, and there's a fixed particle with charge big Q, happens to be 1 microcoulomb, and it's at the origin. See it there, the blue dot? And it's a positive charge. And then there's another particle. It's a very small dot, another particle. It's got mass little q, charge little q, and mass little m, where m happens to be 1 gram. And little q happens to be, based on the animation, negative big Q over 2. And now you also, see all the stuff I'm telling you, and now you also know the initial position of that particle. You see, this is t equals 0, the little particle. It's at x equals 20 meters, y equals 0, and the sliders let you pick the initial velocity. The initial x velocity is 0, and the initial y velocity is 0.5 meters per second. So the way you want to think about this is the little particle, little q, little m, is immersed in the electric field of big Q. Right? Big Q makes an electric field everywhere. Little q is immersed in that. So there's an electric force on little q. F electric equals little q times E. Okay? Where the E is the E due to the big Q. And then we use Newton's second law, A equals F net over M, to figure out how it will move, assuming that the F electric is the only force. I'm going to run it for this set of conditions, and let's just see what the trajectory is. Now, big Q at the origin is nailed down. Okay, it can't move. And little q, remember, has an initial velocity in the plus y direction. So let's see what happens. It started at x equals 20. Well, okay, it went through at about y equals 22. And now negative x of about 25. And now a negative y of about 22 again. but then it's back to where it started. Okay, so it's a closed path, but what is that shape? Turns out that that's an ellipse. Now that's going to be pretty hard to solve for. You wouldn't be able to solve Newton's second law for that. It's pretty messy. But actually, there is a situation we can apply Newton's second law to here that is less messy. What I contend is, if I change, I'm going to reset it. I'm going to change one thing only. V initial y, the initial y velocity. Right now it's 0.5 meters per second. If I choose that initial y velocity just right, I contend I can get little q's trajectory to be a perfect circle. Okay? I want us to calculate what that initial y velocity has to be. All right, let me get back to my OneNote screen so that we can figure that out. Okay? All right, so here's what we know on the animation. The fixed charge at the origin, big Q, positive. And as I said, that charge is fixed. Little q, the little particle's charge, is negative big Q over 2. That's just based on the animation. All right, now, there's the overhead view. There's big Q, dot, 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 going out along the x-axis. There's the little q initially. Okay? All right, let's call that distance there little r, between big Q and little q. So I know there's an electric force on little q. Which way is it? What's the direction of F electric on big Q? Did you say towards big Q? Because they're attracted, right? One's positive and one's negative. All right, now what I'm trying to get here, let me draw part of it. The trajectory, this point, to be a perfect circle. That's just part of it. And I'm giving it an initial y velocity, v initial, y only, straight up in the plane here. I want to find that v initial so that this is a perfect circle, meaning this is a right angle here. Okay? All right, so we're going to use Newton's second law. I'm going to rewrite it like this. F net magnitude equals m times a magnitude. Now remember, if you move in a circle at constant speed, that's what I want, constant speed, with uniform circular motion, the a points towards the center, remember? And that means you need the F net towards the center. Well, that's coming from this F electric. Notice it's towards the center. The center is where big Q is. So the F net magnitude is the magnitude of F electric. And for the A, I'll use our old friend for the magnitude of the acceleration in uniform circular motion. It's the magnitude of the velocity squared over the radius. Remember that little formula? Yep, that's useful. Now, I do want to say a little bit more about F electric. I'm going to think of it this way. It's the magnitude of little q times the magnitude of the electric field. That's the external field for little q, and that means the field due to big Q. So I want magnitude of little q times the magnitude of the electric field from big Q. That'll give me the F electric magnitude. And that's the other side. So that means I'm going to take magnitude of little q. Now, electric field due to big Q. Well, the big Q is actually just a particle. So there's no messy calculation for that electric field. It's a positive particle, positive charge. Big Q over 4 pi epsilon 0 distance squared, little r squared. So that's what goes on the left. mv naught squared over r on the right. I can multiply both sides by one factor of r. And then I can solve for V initial. So all I have to do is divide both sides by m and take the square root. And you get this. V initial, and it will be in the y direction, square root of magnitude little q times big Q over 4 pi epsilon 0 mr. Or, remember, little q magnitude is big Q over 2. So this is big Q squared over 8 pi epsilon 0 mr. And for the big Q, plug in 1 times 10 to the minus 6 coulombs. Don't forget to square that. For the m, plug in 0.001 kilograms. And the r from the animation would be 20 meters. See how far it is initially from the origin? 20 meters. Turn that up just a little bit more so you can see that better. So for the r, 20 meters. So when I plug all those numbers into my calculator and take the square root, I can find what the v initial y has to be. And it has to be just a little bit slower than it was originally. Before it was 0.5 meters per second. Well, it needs to be 0.474 if you're going to have uniform circular motion. So now let's go back to the animation. We've reset it. Now let me set that v initial y with the drop-down menu to 0.474. Hit enter. Okay, that's what it is. And now we'll run the animation and see what we get. See if it's a circle. Started from x equals 20, so we better go through y equals 20. And then x equals negative 20. Yep. And then y equals negative 20. Yep. And then back to x equals 20 again. And there's your circular trajectory. Okay? All right. So that's the kind of thing we also need to be able to do. Right? Predict and quantify the motion that a charged particle is going to exhibit when you immerse it in an external electric field. So those are the main topics for this video, and then there'll be a class video where we'll be practicing. That's all, though, for this video for now.